Not all trusses we encounter in structural analysis are coplanar. Some have a third dimension to the members, and those are called space trusses. So in this example, we're going to determine the forces in members of a space truss, or a three-dimensional truss. The key concepts we're going to use are calculating reactions for space trusses and analyzing space trusses. Specifically, we're going to use the method of joints in this example. Here's our space truss. We're going to determine the force in each member and state whether that member is in tension or compression. It's supported by a ball and socket joint here at A and short links here at B and C. If you remember from statics, a short link means that there's only force applied in the direction of the link. So even though there's a ball and socket back here, we'll only get reactions in the direction of the short link at B and C. So here's our approach. I'm going to start by deducing the sense of the forces in the members. By that I mean we're going to deduce whether the force in the members should be tension or compression, and we'll use that to compare with our answers at the end. We're going to confirm that the structure is determinate, because if it's indeterminate, that changes how we approach structural analysis of this truss. We'll calculate the reactions. We'll apply method of joints in this case, since we need to get the forces in all of the members. Then once we have all those forces, we'll compare the sense of our answers with the predictions we made in step 1, and we'll evaluate if we have a reasonable answer or not. Let's get started. Step 1. We're going to deduce sense of force in each member. So we're talking about tension or compression. So let's take a look. We have a downward force at point E. Member AE and DE are in the XY plane, so they can't resist that downward force at all. So we're going to predict that this member and this member are in tension, or possibly zero, but it wouldn't make sense if we got a compression answer. Now if these are in tension, pulling back towards the XZ plane from E, well, that means that something's got to push point E back out in the Y direction. So we'll predict these two members are going to be in compression in order to balance out those two members in tension. Now let's come up to C. Member BC, AC, and CD are all in the XZ plane. So if CE is pulling out of that plane because it's in tension, that means this link has to be in tension, or pulling back in the negative Y direction. Likewise, here at B, this reaction, or this link, has to be in tension, pulling back that way, because it's the only thing in the Y direction to balance out the tension force we predict in member BE. member AB is the only one that meets here at B that can balance out the downward tension at this joint. So we'll anticipate that this member is in compression. Over here at D, member DE and member AD are both in the XY plane, so they can contribute nothing vertically in the Z direction, which means CD will predict to be a zero force member. Now we said that we predict DE will be in compression, which means it will push back to include back in this X direction. The only thing to resist that is member AD, so it has to pull in this direction. We're going to predict it to be in tension. Now let's look up at C. We predict that member CE will be in tension, so it will pull down. We need something at joint C to push back up. We don't think it's CD. We expect that to be a zero force member. So AC must push up, which means we'll predict it to be in compression. Now what about member BC? Well, we have in the X direction a backward push, or a push in this direction from AC. We have a pull in this direction from EC, so I'm not sure what we'll get here. Once we finish our analysis, we'll come back and compare to all of these, and either they'll match and we're satisfied with our results, or they won't match and we have to decide, did we make a mistake in our calculations, or is there a logical reason that we ignored or missed in this process that would lead us to the ultimate result we got. Let's move to step 2. Let's confirm that this is a determinate truss. Because if it's not, the method of joints is not going to work for us. We need to come up with a different plan. Now our number of unknown reactions: 3, 4, 5, 6. Our number of internal forces, and I'm not going to include the links because we considered them as reactions. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 unknowns internally. Our number of joints: 1, 2, 3, 4, 5. So if we take our unknowns, add them up, subtract our number of equations of equilibrium, and we have 3 to apply to each of the joints, adds up to 0. Therefore it is determinate. So we can proceed with step 3. Step 3. Let's calculate reactions. At the ball and socket joint at A, we'll have 3 force reactions: AZ, AX, AY. At B, we'll have BY, and we'll have BX. At C, we'll have CY. Let's start by summing moments about the z-axis as it runs through point A. And I'll sum all my moments following the right-hand rule, going in the positive direction of that axis. So in the case of moment about the z-axis as it goes through point A, we're talking about this direction about the z-axis being positive. So what contributes? bx and by act through that z-axis, so they contribute nothing. ax and ay contribute through that axis, they contribute nothing. Our force F is parallel, it contributes nothing. So we have cy, it's going in this direction, so it's a negative cy through 8 feet, this distance here, and that's the only contribution. So cy is 0. Now let's sum moments about the x-axis at point A. Again, we're using the right-hand rule, which means things causing moment in this direction about the x-axis will be considered positive. And what contributes? We have no contribution from bx because it's parallel. We do get a contribution from by. It's going in this direction, so it's negative. It is 8 feet from point A. We already said that cy is 0, so it doesn't contribute. All of these pass through the point, so they don't contribute. So we have the downward force, and it is in this direction, which will also be negative. And it's through this distance, which is 8 feet. Solve for by, and we get a minus 600 pounds. We assumed it in the positive y direction, and so it's not. It's in the other direction. Now let's sum forces in the y direction. We'll consider in the positive y direction to be positive for our summation. So we have our unknown reaction ay. We have by, which is a minus 600 pounds, and cy, which was 0. Solve for ay, and we get a positive 600 pounds. We had originally assumed it in the positive y direction, and so it is. Now let's sum forces in the z direction. Again, we'll take positive z-axis as our positive for the summation. Get a contribution from the vertical reaction at A, or the AZ reaction at A. And we have the downward applied force of 600 pounds. Nothing else is in the z direction. So AZ must be a positive 600. We assumed it to be in the positive z direction, and it is. Next, let's sum moments about the y-axis as it passes through point A. So again, we're going to use a right-hand rule. The y-axis as it passes through point A, this will be positive rotation about the y-axis. And so what contributes? Well, cy, by are parallel. They don't contribute. bx contributes, and it is in a positive rotation direction. It's through this distance, 8 feet. None of these contribute because they pass through the point, So we just have our force, and our force acts in this direction, which is negative rotation about the y-axis, and it is through this distance, which is 4 feet. Solve for bx, and we get a positive 300 pounds. And we had assumed it to be in the positive x direction. Now let's sum forces in the x direction. We'll take positive x-axis as our positive direction for the summation. We have ax and the 300-pound reaction at bx. Those are it. So we'll solve for ax minus 300 pounds. We originally had assumed it to be in the positive x direction, and it's not. It's in the other direction. Great. Now we're ready to apply method of joints to find the forces in the members of the truss. Step 4. Method of joints. Let's begin down here with joint D, where there are only 3 members meeting, since we only have 3 equations of equilibrium. We have our z-axis, our y-axis, our x-axis, all here at point D. We have our unknown FCD, our unknown FDE, and our unknown FAD. And this one is in the XY plane. So let's start with forces in the positive z-axis direction. Our only contributor is force CD, so it's 0. Then let's go to forces in the y direction. We'll take along the positive y-axis for our summation. We have the y component of FDE, and that's all. And if the y component of that vector is 0, then the force in that member must be 0. Now we move to forces in the x direction. We'll take in the positive x as positive for our summation. We have the force in member AD, and we have the x component of the force in member DE. But if the force in DE is 0, then the x component is 0. So the force in AD is also 0. So all 3 of these are 0. Now let's move to joint C. Why? Because we know already that this force is 0, this reaction is 0, and that leaves us only 3 unknown member forces at joint C. So again, we have our z-axis, our y-axis, our x-axis. We have our unknown force in CE. We have our unknown force in AC. And we have our unknown force in the x direction BC. And AC acts in the XZ plane. CE acts in three-dimensional space. Let's start by summing forces in the y direction. Again, we'll take the positive y-axis as positive for our summation. We have a contribution from member CE, and that's it. So if that component of the vector is 0, the force in member CE is 0. Now let's sum forces in the z direction. We'll take the positive z-axis direction as positive for our summation. We get a negative contribution from member AC and a negative contribution from member CE, but we know that that member is 0, so that leaves only the z component of force AC, and if that component is 0, the force in the member must be 0. Last one, force in the x direction. We'll take positive being in the positive x direction. We have the force in member BC. We have components from AC and CE. However, there's 0 in the member, so the components are 0. So our only contribution is BC, and therefore it is also 0. Now let's move to joint A. I know that this member is 0, and this member is 0. I know the reactions at A, so there are only 2 unknown member forces at joint A. Our z-axis, our y-axis, and our x-axis. We calculated our reactions to be at A to be 600 pounds in the positive y, a negative 300 pounds x, and 600 pounds z. We have our unknown force in member AB and our unknown force in member AE. And member AE is in the XY plane. Let's start by summing forces in the z direction. We'll take positive z as our positive for the summation. We have the force in member AB. We have the 600-pound reaction in the positive z. Those are the only 2 contributors. So the force in member AB is minus 600 pounds, which means it's 600 pounds compression, because we drew it pulling on the joint, which implies that it was tension. Next, we're going to sum forces in the y direction. And to do that, let's take a look at member AE, and we need the length of that member. And we get that by squaring all 3 vector components of its length, and the z component of its length is 0. Take the square root of that summation, we get 8.944 feet long. And that'll be important when getting the components of force in AE. So in the y direction, we take positive y-axis as positive for the summation. We have the 600-pound reaction at A, and we have this portion of the force vector. So we get 8 over 8.944 times the force in member AE. Those are the only contributors. So the force in member AE is a negative 671 pounds, which means it is 671 pounds compression, because we drew it pulling on joint A, and that implies tension. Now let's go to joint B to get our last unknown member force. Our z-axis, our y-axis, and our x-axis. We have our two reactions at B, negative 600 pounds in the y direction and a positive 300 pounds in the x direction. We already calculated that the force in member AB is negative 600 pounds. And we have an unknown force in member BE that we're looking for. And member BE points off in three-dimensional space. So to find it, we're going to need the length of member BE. So it has an x component of length of 4 feet, a y component of length of 8 feet, and a z component of length of 8 feet. We take those squares, sum them each up, we get 12 feet for the length of member BE, and that'll be important in our summation. We're going to apply equilibrium in the z direction. We have drawn downward a negative 600 pounds, so that member in force, the force in member AB will actually be up, and then we have a negative component force in a member BE, and it's the z component, so it's 8/12 of that force in member BE. We solve for the force in member BE. We get a positive 900 pounds. We drew it pulling on the joint. We got a positive, so it's in tension. We've found all of the unknown member forces, but we've not applied equilibrium to joint E yet. So let's use that as a check of our work so far. So we have joint E, z-axis, y-axis, x-axis. We have the applied load of 600 pounds down. We have force in member CE, which was 0. Force in member DE, which was 0. We have force in member AE, which we calculated as minus 671 pounds. And we have the force in member BE, which we calculated as a positive 900 pounds. Remember, the 900 pounds is in three-dimensional space, but the 671 is in the XY plane. But some forces in the X direction. We'll take positive as being in the positive X-axis direction. We have (4 over 8.944) times the 671 pounds in member AE, and we have 4/12 of the 900 pounds in member BE. 4 for each of those being because of the X component of their length. Add those up and we get 0, as we should if it's in equilibrium. Good. Now let's check forces in the Y. In this case, we're going to get a negative contribution from the force in member AE. It's 8 over 8.944 times the minus 671 pounds. We'll get a negative contribution from member BE, and it is also 8 is its length component times the 900 pounds. Put those together, and again we get 0. That equilibrium checks. Now let's sum forces in the Z direction. We have our downward applied force of 600 pounds. There's no contribution from member AE, but we do have 8/12 of the 900 pounds contribution. Add those together and we get 0. So our equilibrium checks at joint E. That's a good sign. Now let's go back and compare with our predicted sense of the forces in the answer. Step 5. Let's compare with our prediction. But before I do, let's show a summary of the forces we calculated. We found this link to have 0 force in it, this link to have 600 pounds in it, and in terms of sense, that would be tension because it was in the negative Y direction. This link we found to have 300 pounds, and again in a sense it was in tension. At A, we had a Z reaction of 600 pounds up, an AX reaction of 300 pounds in the opposite direction, and an AY of 600 pounds in the positive Y direction. We found member CE to have 0 force in it, CD to have 0 force in it, DE 0 force in it, AC 0 force, BC 0 force, and AD 0 force. We found member AB to have 600 pounds, and it was in compression, member AE, 671 pounds. It too is in compression. And member BE, 900 pounds. It was in tension. So let's go back and take a look at what we had originally predicted. The members that are not zero force, we were consistent. We had predicted compression here, and tension here, and tension in this link. Now what we failed to recognize in our original prediction was that all of these members would actually be zero force. And that's an acceptable something to miss. But if we had calculated that the signs changed, then we'd have to look very closely at what went wrong. So we're able to conclude it compares favorably. But we missed prediction of some zero force members. But that doesn't lead me to believe that we've made a mistake. Remember, we checked equilibrium at joint E, and that worked out. None of our predicted senses were opposite from what we calculated. So we have reason to believe that we have reliable results shown here. Now let's go back and review the process we followed. We started by predicting the sense, tension or compression, in each member so that we'd have something to compare at the end. We then confirmed that it's a determinate truss because that would change our approach otherwise. Once we knew it was determinate, we calculated the reactions using equations of equilibrium, and we began applying method of joints. We started at joint D because there were only 3 members meeting at that joint, found that all 3 of those members were zero force. We then moved to joint C where there were only 3 unknown members, found that all of those were also zero force. We then moved to joint A where there were only 2 unknown members, and we calculated those. Both of them turned out to be in compression. We then moved to joint B to get our last unknown member force in member BE, and it turned out to be in tension. And then we went to joint E as a check, and each of the 3 equations of equilibrium turned out to be 0. We then summarized all of the calculated results, compared them with our prediction, and concluded that we have reasonably predicted the force in each of the members and determined whether they would be in tension or compression. Well done.